There aren't many tools when it comes to dealing with general metric spaces, and that makes the few that we have very important and universal. And one of those important cornerstone results is what is called Vitali covering lemma due to Vitali, or the 5R covering lemma. Let's read the statement and then we can discuss a little bit about the details and intricacies. We are in the setting of a separable metric space, a metric space that has a countable dense subset. There is a sequence of elements in the space x1, x2 to infinity so that its closure is all of the space. This is basically saying that the space is not horribly large, but it still contains many familiar examples. All Euclidean spaces are separable and for example, Heisenberg groups are, and so on. Let F be a collection of closed balls in a separable metric space so that there is an upper bound on the diameters of them. Then you can find a subcollection G that is countable. Although the original F could have uncountably many balls, G has at most countably many. The balls in G are disjoint. If you pick B1 and B2 from G, then their intersection is empty. And most important of all, the balls in G do most of the job. If you dilate them by 5 times, they cover everything that the original collection of balls covered. Namely, if you take the union of all balls from the original collection, you lose nothing if you take the collection, the union over balls in G only. Of course, provided that you dilate them by the factor 5. The notation, just to be clear, a closed ball is defined this way. It's not closure of the ball. By its definition, it includes these points. So in general, this is not the same as closure of the open ball. And 5 times a ball means the same center, but 5 times the radius. All of these make sense on general metric spaces. By the way, the theorem will be true if you replace this closed with open. If you take all of them open, the proof goes through. If you take all of them closed, the proof goes through. I haven't checked really what happens if you have a mix of them. Probably still good because we're not optimizing this constant 5. With this 5, you can replace it by anything bigger than 3, by the way. Okay, here's a very basic picture. Of course, I can only draw finitely many balls in finite time. And suppose F is this collection of blue balls here. The theorem says that there is a subcollection of them that are mutually disjoint. For example, if you choose this ball, then you're not allowed to choose this ball. By the way, the interiors of these balls are also included, but of course I would have made a mess by filling them in. So it's not just the perimeter. Okay, so these elements in G are to be disjoint, and once you fix your choice of G, if you dilate the balls by 5 times, you cover everything. Probably in this picture, it would be the case that none of these balls from top here, if dilated 5 times, would be enough to reach these balls here. So you have to pick one of these guys. And again, because you are dilating by 5, you can take the bigger one or the smaller one. I would prefer to take the smaller ball because if I dilated 5 times, I'm definitely not getting into any trouble with the stuff from top. Actually, that doesn't matter. We don't want 5Rs to be disjoint, but still, this kind of seems like more optimal choice for that. So definitely, you will need one of these from down here, but from top here, maybe you can pick, excuse me, maybe you can pick this one here. If you dilate it 5 times, maybe it reaches somewhere around here and everything here. So then you can pick, for example, this one here. It's definitely this one and this one are disjoint. And if you dilate this 5 times, then it helps to cover the rest of this. So with this ball, 1 here, 2 here, and 3 here, you can do the job. So out of these many balls, which I haven't counted, only 3 for G are sufficient. But the theorem says that you can do it all the time. In any metric space where balls can have crazy shapes, the collection you start with could be allowed to be uncountable, but still all of this goes through. The proof of this theorem is quite easy, and that's what we will present first, and then we will go to show one typical application of this lemma, which I think will be enough to convince you how this is used and how important this lemma in general becomes. Okay, so for the proof, the data we start with is of course the metric space X that is separable and the collection F. Okay, so we first order these balls according to their diameter. So F1, for example, becomes those balls in F in my collection such that its radius is less than or equal to R. So remember, R is the biggest. No ball has a strictly larger diameter radius than R. So maybe I should switch this to radius because it's just easier to do with radius. And then bigger than 1/2 of R. There is nothing significant about this 1/2, and that's the reason you can replace 5 by 1 plus 2. So you can put any number like 1 over C as long as it's C bigger than 1, and that proof will give you 1 plus 2C in the place of 5. So the smallest is 1 plus 3 plus just a little bit. You cannot hit 3 itself, but anything bigger than 3 will work. Refer to Wikipedia for details. So the Wikipedia article are usually very good on more known results, and this is no exception, so I really recommend reading that as well. Okay, so maybe not all balls in the original collection F have radius in this range. That's why we also need F2 to cover more. So then everything that is not in the first collection will have radius less than or equal to R over 2, but some of them will have more than 1/4 of R. And then you get the idea. So we inductively define Fn to be the collection of balls such that it's R over 2 to n minus 1, because 1 had 0 in here, and bigger than R over 2 to power n. So obviously the original collection is just union of Fn, because, well, a number less than R will be between R over 2 to n minus 1 and R over 2n for some n. There is no claim yet about disjointness of anything, except that if you are a ball and you are in F2, then you are not in anything else. That's for sure. Okay, then out of these we begin to construct our collection. So we let G1 to be A, so this A here is so important that I rush to write an A instead of E for B. So to be A, not the, a maximal collection of disjoint balls in F1. Now just focus on F1. There could be uncountably many balls here. Maybe all the balls actually have radii in this range. In that case, F1 is just all of F. What we know for sure is that you can pick a collection, a subcollection that are disjoint, and it's maximal in the sense that you cannot pick any one more from F1 and add into G1. It will then touch something you have already picked. So maximal in that sense. Why can we pick such a thing? Zorn's lemma. Maybe it's an overkill, but if you are dealing with uncountable general stuff, maybe that's unavoidable at the same time. So out of the balls whose radii are quite large, so you can say that these are the big ones, the bigger balls, and as you go down you pick finer and finer collections, sub-collections from F1. But out of the biggest guys in the original collection, you're picking a maximal sub-collection. And suppose you have, so this is an inductive construction, suppose you have constructed G1 until Gn. So to choose Gn plus 1, first, so to choose G1, what you do is the following. First, you throw out those B. So this Gn plus 1 will be a subcollection from Fn plus 1, but some of these could already have been basically picked up with the previous ones. So you throw out those B in F1 for which there exists some ball in Gi for some I from the previously picked collection, for which there exists some C, some ball from previous collections that intersects B. Okay, so out of the bigger balls, you have already picked some nice ones. So GIs are going to be our nice disjoint collections. Now you are trying to choose a nice subcollection from these balls, but some of these could have intersection from the previous chosen ones, and if you choose any of these, then your collection G's will no longer be disjoint. So that's why first of all you threw out these. From the remaining, which could be empty, maybe nothing remains here, in which case you will move on to the next step. So from the remaining balls, you choose again a maximal. So this kind of proves, the reason actually I include this proof is to demonstrate how flexible the proof is, because it's not too delicate. It's not saying that there is a unique way of doing these. So in each step you have some choice, and that means you have a lot of different ways in general to choose this subcollection. So you choose a maximal subcollection Gn plus 1. So basically, again, Gn plus 1 is a maximal disjoint subcollection from fn plus 1, but you needed this modification just to make sure that you don't pick too many. Okay, the claim then is that, okay, so we inductively constructed GNs. If you pile them up, is the right subcollection as in the conclusion of the theorem. So this is that subcollection that we were looking for. So what properties did we want for this? Let's check. So balls in G are pairwise disjoint. Why? Okay, if you choose two balls from the same eye, so B1 from GI, B2 from GI, then what was GI? GI was chosen to be a disjoint subcollection, so they have no intersection. What if you choose B1 from G1, GI1 and B2 from GI2, and you can imagine that I2 is bigger than I1 without loss in generality. Then remember that to choose GI2, first we threw away from FI2 everything that intersected with previous collections in G. Therefore, whatever is chosen here will have no intersection with anything chosen from GI1. In particular, B2 will have no intersection with B1. So this property checks is disjoint. Another property is that G is countable. Okay, this will of course follow if we say that GI is countable for each I. But actually I don't need that even. The reason being, so I leave this as an exercise, in a separable, so that's the only place where separability is used, in a separable metric space. Indeed, if you drop countable from the assumptions and drop the requirement for countability from the conclusion of the theorem, you again have a theorem with the same proof. So in a separable metric space, any collection of disjoint balls is at most countable. By the way, I'm not counting degenerate balls here, so balls must have positive, strictly positive radius, no zero. And that's an easy exercise. Maybe easy once you discover it. There may be different ways of doing it. There is a tricky, nice one right there. Put it in the comments if you discovered that. Just double check maybe. Okay, so B, the collection G we have found has the two basics. They are disjoint balls. We haven't picked unnecessary balls. Number two, we haven't picked too many. It's countable. So number three, the last requirement which we have to check is that union of balls in F are covered by union of 5 times balls from G. So how do you prove this thing? So it's enough to show that every ball is contained here. So pick some ball in F. We must show that this B is in this 5B, B in G. Okay, there exists some N. Actually, there's a unique N such that this radius of B is between r over 2 to power n minus 1 and r to power 2 to n, of course, which means that B belongs to Fn. Okay, if B was chosen in Gn, we are done. That means B itself is one of them, and actually now B owes us something because we have dilated it by 5 times. So we really have covered that ball. So the remaining case is, if B is not Gn, then since Gn is maximal, the best we could try, we picked as many as we could without running into intersections, and B was not chosen. That means there exists some C in Gn such that C intersection with B is not empty. Otherwise, we could just toss this B into the collection Gn. That would still be a collection of disjoint balls, and it would be bigger than the collection Gn, which then contradicts the maximality in the choice of Gn. So that contradiction shows that if B was not chosen in Gn, that's because some other ball from Gn must have intersected it. But then this ball that wasn't chosen has to be contained in 5 times that ball which was chosen. And the proof of that is just a beautiful triangle inequality picture. Okay, so this is suppose the ball C that was chosen, and this is the ball that was not chosen. To make things work, I want to make C's job the most difficult. C is trying to make this happen. If you dilate it 5 times, it has to consume B. To make its job the most difficult, I'm putting it outside, of course, as far as I can. But it's still, they meet, so I made it just touching along the boundary. Then what happens? What happens is that the worst point, the farthest point here, how far that point can be to the center of this one. So suppose this is the center of this other ball B. Okay, let's look. Distance of x, y is less than or equal to distance. And make sure that I'm not cheating and I'm not assuming any Euclidean structure. Of course, my picture is like that, but imagine this is a metric space. Balls can have very distorted shapes. Balls don't even have to be connected sets. But what I'm writing is true because it's only triangle inequality. So this will be, there is some point where they touch, which I call it maybe P. So this will be x and P plus distance of P from Z. I'm using triangle again, yet again, Z and Y. But, okay, the balls B and C belong to Fn. That means the radius of this thing. So this means radius of B. Remember, Fn is allows for 1/2 or twice range. So the diameter, the worst versus the best, the largest diameter versus the smallest diameter of balls in Bn can differ by only a factor of 2. So again, let's say C is much, the worst that it can be in being smaller than B. So let's say, what is distance of x to P? This is a point in the ball C, and this is the center, so it's at most radius of C. Then each of these guys is, this is the center, and these are points in the ball, so each one can be at most radius of B, and this is 2 times. Okay, and then this will be radius of C plus radius of B, we said can be bigger than radius of that, but at most 4 times. So 4 times radius, 2 times. So radius of B is at most 2 times radius of C. So that makes it 5 times radius C. And that's why where this 5R covering lemma comes in. So every point, every random point in the ball B has distance to the center of C at most this value. So this is for every Y in B, that means B is contained in ball. Distance of every point to X is at most 5 times radius C. Oh, okay. I messed up the notation. 5 times C. Okay, that's the proof showing that, yeah, every ball is contained here. The proof, although maybe lengthy, was very simple. We know B is in some Fn. If B is in F, that means it's in some Fn. So the analysis just reduced to that range. The help from Fn was that the largest ball in Fn versus the smallest one, their radius can differ by a factor of 2 at most. And that played a big role. Yeah, and then the rest of the proof in this picture, and just triangle inequality. Therefore, this third property also checks. We have a subcollection that is disjoint, countable, and the covering property. And that brings us to the end of the proof. As I promised you, I want to show, without further details, just a quick application of that. First, there are some good pictures on Wikipedia where you can read more about this, about countable versus uncountable, this sharpness of 5. Okay, so the application that I want to show you is to what we call Hardy-Littlewood Maximal function. The way it works is that for an integrable function, you define the largest average over balls centered at X that you can get. So maximal function f evaluated at X is the largest average value for f, for absolute value of f in fact, that you can obtain over balls centered at X. A very, very important result in analysis is that this operator that takes a function f to the function mf is a bounded operator on Rd. That means there is this constant c such that the LP norm of mf is bounded by c times the LP norm of the original f. That is here called strong type estimate, but to prove that, one first establishes the weak type estimates, and that is saying that the measure, so here absolute value sign around the set means just the Lebesgue measure. The Lebesgue measure of the set of points where mf function is bigger than lambda is less than some constant over lambda times the integral of f. So where does Vitali covering theorem come in to improving such a result? maybe here again, the picture will help. So suppose this is RD, and you have a function from RD into R. If you're not familiar with LP or measurable functions, just think of a continuous function because it's mostly the same. So this is finite. So this is called, if you take root 1p root of that, this becomes the LP norm of f. So this is just LP norm of f to power p is this quantity. We know that is finite. Now, the claim is that the Lebesgue measure of the set of x in Rd, where this maximal function evaluated at x is bigger than lambda, is less than something. So the theorem is that there exists some c positive such that c, and then this will be norm of f LP. Okay, so as I said, I don't want to get into too many details. So what does this quantity say here? What does this say here? By definition, this is the, let me write mu for the Lebesgue measure. That's just easier notation. So MF is the supremum over all radii of the average value of f. So here's x. You take a ball of radius r, and you take the average of f on that ball. And that you play around with the radius to get the supremum. And that supremum is bigger than lambda. This would mean that there is some radius for every x that you pick in this set. There is some radius, which depends on x, by the way, such that integral over that ball, radius x and r, of f d mu, 1 over measure of the ball, same ball xr, is bigger than lambda. So for every x, this is true. Maybe there is another x here, and with this different radius where this happens. Maybe for this x, there is this huge ball here that happens. Maybe here there's this. But what we know from definition is that for every x that happens. We want to estimate the measure of the set. The problem is that these balls definitely, most likely, are not going to be disjoint. And if we just added the measures of them, we're overly adding them maybe infinitely many times. That's where the Vitali covering comes in, and it shows that there is just a certain subcollection that are disjoint, and if you dilate them by 5 times, you cover your set. So that at the end, you end up with some calculation like this. So measure of this whole set, where MF is bigger than lambda. Okay, this is covered by measure of union of 5 times these balls, these special balls. I know you have only countably many of them. But then from the property of measures, this is less than the measure of individual ones, 5bi, and then I goes to 1 to infinity. But then the Lebesgue measure is homogeneous, that it multiplies the radius by something to power. So this will be 5, in this case, to power d, measure of bi. You put this 5d outside, and then you end up with measure of bi. And now comes the fact that bi's are disjoint. So by doing this trick in these 2 steps, 5 bi's still can overlap, but bi's by the conclusion of Vitali covering are disjoint. That means this is 5d, measure of the union of bi's. And then the rest of the story. And then you use this defining property here, so you put the measure here, and 1 over lambda goes under this. So I think here we don't go this way. Actually, measure of bi is less than, okay, here is how you use it. So by definition, this is 1 over lambda integral over bi of f. Okay, now you use the fact that these are disjoint so that the integral, instead of having the summation, you can have union. So this will be over lambda, and then this will be integral over union of now bi's, because you know they are disjoint, and that's very important. Otherwise, you cannot do that. And that's pretty much this inequality we have here. Of course, there are details like why is the supremum of the radius bounded. That is a necessity. But in general, this is the typical way in which covering lemma is applied. So every time it's applied, it's one way or other similar to the thing that I just showed you. Okay, so that brings us to the end of the story of Vitali covering. Let me know if you enjoyed this proof. Answer the questions I asked. Why you have countable many, and yeah, hope to see you in future videos.